All right, so our last problem solving tip is using approximation. Um, why do we want to approximate things? Well, in a lot of cases, we might have a really difficult problem, either that requires a lot of thought or maybe a lot of data collection in order to solve it. And we want to know beforehand what you kind of in what area is that answer going to be. It's possible that all that data collection might reveal that this problem is not really useful to us, and so we can save a lot of difficulty by finding out that ahead of time. Or it might be that approximation points out an error, right? If our approximation and our final answer are way off, we might have made a mistake in that long, difficult problem. So let's talk about how to do some approximations. If we have this jar full of M&Ms, how many M&Ms are in there? I don't know, 1,000, 200, a million? When we do that, you see the jar and you make a guess like this, um, people are often just sort of taking a number off the top of their head. Well, we can do better than that, right? So what do we need to know? We need to know what the volume of our jar is, and we need to know what a volume of an M&M is, and not a Skittles, even though there's a Skittles bag here. These are M&Ms. Otherwise, it wouldn't be worth knowing anything about them. So we can make some guesses, right? So our Skittles bag, you might figure that's about 10 centimeters long. So our jar here is 30 centimeters, has a diameter of about 20 centimeters, roughly. And maybe we're off a little bit, but we're just trying to find what's called an order of magnitude answer. Like, is it within, we don't want an answer that's 10 times what it is or 10 times, less, but somewhere, 2 or 3 times off, we're okay. So we take the volume of the jar, which is just our height times our radius squared times pi, right? Because this is the equation of a circle, r squared pi r squared times the height. This is the volume of a cylinder. We throw in some rough numbers, right? 30 centimeters times 10 squared times pi. For those of you taking the MCAT, you know that one of the things you need to get better at is just doing this kind of stuff in your head, right? So you want to practice that. That's the only way to get better at this. So we figure this value here is about 100, right? So this is 30 times 100. So that's going to be 3,000 times pi, which is about 3. So we're going to get about 9,000 centimeters cubed. It doesn't make sense to come up with a more exact answer because these numbers are approximations, right? We don't really know, is it 31 or 34 centimeters? We don't know. So any, more than one significant figure here really doesn't help us. So we can then model our M&M, maybe it's a centimeter by half a centimeter. So we can find the volume of that. And then all we have to do is figure out, well, how many of these fit in there? About 18,000, okay? Is that right? I don't know. But if I ended up counting them, or used some other, some kind of M&M counter to figure it out, and I got the answer 200,000, I'd think that something was wrong with that M&M counter. Or if I got the answer 1,000, I would think that something was wrong. And I'd have to double check my work. So that's the usefulness of approximation. I'm going to stop talking. So here, I'm not going to go through this step by step, but this is a famous approximation problem. Sometimes these are called Fermi problems, after the physicist Enrico Fermi. And this one's kind of famous in part because the question is, how many full-time piano tuners are there in Chicago? I have no idea, right? You have no idea. And the idea here is that with some good guesses, or not even necessarily great guesses, we can get an answer that's pretty close to the truth on an order of magnitude. In other words, within 2 or 3 times of being correct, not being 10 times off or 100 times off. And so you follow these steps. They're kind of interesting. Each of these is a guess, right? How many people are in Chicago? I don't know, 9 million, right? How many per households, right? Figure out how many households, figure out how many pianos there are, how often do they get tuned, and you come up with an answer here, which as it turned out, I can't remember what year this problem was, um, Fermi introduced this one, but I think this was his. Maybe not. Maybe I've just connected it in my head. But the answer was something like 200, right? So you're in the ballpark, even though you start off thinking, I have no idea what the answer is. And so a good approximation can get us close to the answer, can give us a good ballpark answer. So why are these problems useful? They're useful because thinking in those broad strokes can help guide our solution process. It can help us determine what tools we need, right? What kind of instruments, how accurate do we need to be? It can help us give us a benchmark to catch errors. What that means is, once I do this problem, I expect to find an answer about 200 meters per second, right? And I find an answer of 1.5 meters per second. You think, okay, something's wrong here. Maybe made a math mistake, used the wrong equation, but something got me the wrong answer. And then in the real world, in things like engineering or health sciences, you can decide whether even a problem is worth approaching, right? Maybe a quick back of the envelope approximation tells you it's going to be way too expensive for the benefits that you're going to get, okay? Or some change you're going to make in a process is going to make a really tiny change to your end result. And then you say, oh, well, maybe we don't need to do that. We don't need to spend any more time on that. And so that's why approximations can be really useful.